An extraordinary figure is capturing the attention of operational forecasters today: 90 million. This is not the number of people in the path of a singular event like a tornado outbreak or a hurricane. Instead, it describes the population residing within a vast, severe weather corridor stretching from west central Texas up through the Ohio Valley and lower Great Lakes and into northern New York and Vermont. At the same time, another 90 million people, with significant overlap, are situated inside a mid-Atlantic heat dome where temperatures a mile above the ground are running 2 to 3 standard deviations above normal. This is producing record-setting highs in the mid to upper 90s along Interstate 95 from Washington to Boston. Remarkably, a single Rossby wave is driving both phenomena. What follows this event, a 25 to 30 degree temperature crash in the subsequent 48 hours, is a story that is not yet being widely told. If this is what one atmospheric wave can do on May 19th, we must ask what the atmosphere is now calibrated to produce. If this complex story has captured your attention, we invite you to join us on Calm Space as we continue to explore these powerful events together. There are days when the National Weather Service issues a handful of alerts, and then there are days when the nation's entire weather enterprise seems to align in one direction. Today is one of those latter days, and the sheer scale of what is happening is difficult to convey with a single number on a map. As this script is being recorded, 90 million Americans are within a severe weather corridor that extends from west central Texas all the way to Vermont. Simultaneously, a largely overlapping group of 90 million people is inside a heat dome, generating record or near-record temperatures from central Virginia to Boston. The atmosphere is orchestrating two immense and distinct events on the same continent during the same week of May, and it is accomplishing this with a single atmospheric wave. The number that has become a touchstone for this event is 90 million. It is the figure that forecast offices, the Storm Prediction Center, and broadcast meteorologists are all converging on, as it offers the clearest way to describe a corridor of risk that does not respect the boundaries between different weather categories. The Storm Prediction Center has issued a slight risk severe weather outlook for today that carves a path from west central Texas through the Ozarks, the Tennessee and Ohio valleys, and across the lower Great Lakes before curving north into western New York and Vermont. This represents one of the largest single-day severe weather footprints the agency has issued for mid-May in recent years. Within this zone lie major population centers, including Dallas-Fort Worth, Cincinnati, Indianapolis, Columbus, Cleveland, Detroit, Toledo, Buffalo, and the cities of upstate New York and northern New England. Within the overlapping heat dome footprint are New York City, northeastern New Jersey, Philadelphia, Baltimore, and Washington, D.C., as well as the entire central Virginia Piedmont and the Connecticut and Merrimack valleys of southern New England. When viewed together, this combined area of atmospheric stress covers roughly half the population of the United States. The sheer scale of this combined footprint illustrates how interconnected our continent's weather systems truly are. What distinguishes today from a standard severe weather day or a typical early season heat event is that it is both, occurring at the same time and produced by a single upper-level pattern. A deep trough sits over the western United States, while a strong upper-level ridge is anchored just off the southeast coast. Together, these two features form a single Rossby wave configuration that is doing all the atmospheric work. The trough is generating the western part of the story, providing the trigger for severe weather as a cold front pushes into the warm sector. The ridge is producing the eastern part of the story, which is the heat dome. The wave between them creates the energy gradient that drives the entire system forward. This is not a normal mid-May setup. It is a display of the operational maximum that a single Rossby wave can produce on one calendar day, on one continent, at this point in the year. To understand how truly unusual this is, we must examine the magnitudes that National Weather Service offices are using to describe what they are seeing. In its afternoon discussion, the Boston office placed 850 millibar temperatures over southern New England in the range of 18 to 20 degrees Celsius. For those not familiar with meteorology, this is the temperature about a mile above the surface, and it is the variable forecasters watch to know how hot a column of air can get when mixed down to the ground. In the climate record maintained by the National Centers for Environmental Information, which runs from 1979 to the present, the normal 850 millibar temperature for this calendar date over southern New England is typically around 8 or 9 degrees Celsius. Today, it is running at more than double that value. The Boston office classifies this departure as 2 to 3 standard deviations above the climatological average. These are not just numbers on a screen. They are a measure of an atmosphere under immense strain. A 2 standard deviation event is expected to occur only about 5% of the time on any given calendar date. A 3 standard deviation event is far more rare, occurring just 0.3% of the time. For the May 19th calendar position, with an empirical baseline stretching back 47 years to 1979, a 3 standard deviation event would be expected at any single station about once every 300 years. What the Boston office is describing today is not a single station. It is a coordinated 2 to 3 sigma signal across multiple stations over a multi-state region all at once. The Baltimore-Washington office, in a forecast discussion issued before 10:00 inches the morning, described another day of challenging record-high temperatures, all due to the strengthened upper-level ridge. The office noted that 850 millibar temperatures over the mid-Atlantic would be even hotter, running in the range of 19 to 23 degrees Celsius, further underscoring the intensity of this continental scale event. An unusual wave of early season heat is descending upon the eastern United States, with forecast offices projecting high temperatures between 96 and 98 degrees Fahrenheit. This warmth is stretching from the central Virginia Piedmont all the way up through the major metropolitan areas along Interstate 95. The Mount Holly, New Jersey office, which oversees the Philadelphia region, has already described the day as one of record-setting, early season intensity. Further north, the New York City office on Long Island has taken the step of issuing its first heat advisory of the year, a measure affecting northeast New Jersey and the New York City metro area. This advisory is in effect from 11:00 inches the morning today until 8:00 inches the evening on Wednesday. What makes this advisory particularly noteworthy is the language used to justify it. Forecasters have flagged this as the first high heat index event of the year, a specific operational phrase that signals a crucial shift in focus. It indicates that the primary concern is not merely the meteorological data, but the human physiological response, the fact that people's bodies have not yet had the chance to acclimate to the stresses of summer. The arrival of the year's first major heat event in the largest metropolitan area in the United States on May 19th is, in itself, a significant anomaly. Historically, the New York metro area does not typically experience conditions warranting a heat advisory until the middle or even the end of June. For such an event to occur more than a month ahead of schedule is remarkable. This deviation is compounded by the intensity of the heat, which is climbing into the mid to upper 90 sets, far exceeding the low 90s that usually characterize the first heatwave of a season. This combination of premature timing and elevated temperatures transforms what might have been an interesting weather day into an operationally rare phenomenon. But this dome of heat is only one side of a much larger atmospheric story. To grasp the full scope of what is unfolding, we must look to the west. The corridor of severe weather and the dome of intense heat are not two separate coincidental events. They are, in fact, two distinct expressions of the very same upper-level atmospheric pattern. Both are manifesting on the same day, driven by the same fundamental physics. This is the signature behavior of a high-amplitude Rossby wave when its phase position aligns in this specific manner. If one were to trace a single line on a forecast map from Galveston, Texas to Maine, it would intersect nearly every category of operational weather warning issued by the National Weather Service. This path would cross flood warnings along the lower Mississippi, through central Missouri, and into Indiana. It would then traverse the severe weather corridor, stretching across the Ohio Valley and into upstate New York, followed by the belt of heat advisories along Interstate 95. Finally, it would encounter marine warnings off the New England coast, small craft advisories on Long Island Sound, and the approaching cold front trough expected on Wednesday. One line, drawn across a continent, encapsulates a continent's worth of weather. This is the operational reality of the day. It is crucial to understand that for the operational forecasting community, today's events are not a surprise. The complex sequence of weather we are witnessing is the climax of a pattern that has been clearly visible in forecast models for the better part of a week. The Storm Prediction Center identified the underlying threat pattern days ago, and for the past 48 hours, National Weather Service offices in the Mid-Atlantic and New England have been steadily escalating the language in their heat advisories. Forecaster discussions from offices like Mount Holly, Baltimore, Washington, and Boston have all pointed to today and tomorrow as the verification days for a pattern that began organizing itself last week. The atmospheric science community has been watching this build, fully aware of what today represents. But the truly compelling part of this story is not just what is happening now, but what is set to happen next. The same atmospheric wave producing today's dramatic weather will behave in a way that many might not anticipate on Thursday and Friday, a development that forecasters are monitoring with great care. The atmosphere reaches its peak intensity today. On Wednesday, a cold front will sweep through, and in the 48 hours that follow, temperatures along the entire eastern seaboard are predicted to plummet by 25 to 30 degrees Fahrenheit. The heat dome responsible for today's record numbers will not gradually weaken over a week of warm days. Instead, it is forecast to collapse abruptly over just 2 days. What follows this collapse is the part of the story that is not yet being widely discussed. In their technical discussions, which are publicly available on the National Weather Service website, operational forecasters are using a specific phrase to describe the coming period, not very favorable for organized severe weather. This forecast suggests that the synoptic environment between Wednesday's cold front and the next anticipated window for significant, organized severe weather is expected to be unusually quiet. That next window is not projected to open until approximately May 25th through May 28th. This implies nearly a week of large-scale atmospheric silence, immediately following a 4-8-hour multi-hazard pulse of extreme weather. Today represents the maximum, and the week that follows may represent the quiet. This stark contrast between intensity and calm is the second half of the story we are exploring. It also raises a profound question that frames our entire inquiry. If a single Rossby wave is capable of producing today's conditions on May 19th, during a year when the El Niño Southern Oscillation Index is still officially neutral and only just beginning to lean toward El Niño, what could a similar Rossby wave configuration produce later in the year? What might it be capable of in October, or December, or the months that follow, when the global climate state is more energetic and the temperature gradient between the equator and the poles has shifted? Today serves as a form of calibration. The atmosphere is demonstrating its capabilities at a specific point on the calendar, the 19th of May, 2026. The question that naturally follows is what it might be capable of at later positions on that same calendar, within the same year, but under a different set of global forcing conditions. This is the question to hold in mind as we delve deeper into the data of what is actually happening today. As 90 million people experience a Tuesday evening unlike any other. To truly appreciate the significance of this event, we must spend a moment with the number itself, 96 degrees Fahrenheit. This figure carries a different weight in May than it does in August, a fact that operational forecast offices are keenly aware of and are incorporating into their public discussions. For the remainder of our exploration, we will adopt their framing, as it offers the most insightful perspective on why this early heat is so important. It is a lens that helps us understand the deeper meaning behind the numbers on the thermometer. A temperature of 96 degrees Fahrenheit on August 15th in Washington, D.C. is certainly a hot day. Under the right conditions, with a high dew point driving the heat index above 105, the National Weather Service would likely issue a heat advisory. But what if that same 96-degree reading occurred on May 19th? The meteorological data point is identical, yet the situation is entirely different. The crucial variable is not the weather, but human physiology. Our bodies possess a remarkable cooling system, relying on sweat and the dilation of blood vessels to dissipate heat. However, this system is not static. It acclimatizes to recent conditions. In May, a population accustomed to temperatures in the mid-70s is suddenly asked to endure the mid to upper 90 seconds. The body's cooling mechanism, which should spring into action, cannot operate at full capacity because it hasn't been calibrated for such an extreme shift. The result is a lower sweat rate, a slower vasodilation response, and a reduced threshold for heat stress. This subtle biological lag means that 96 degrees in mid-May is medically more dangerous, degree for degree, than the same temperature in mid-August. This understanding of acclimatization is not just a theoretical concept. It is actively shaping how forecasters communicate risk. Take, for instance, the area forecast discussion from the New York office, issued at 10:37 a.m. Eastern Time. The initial paragraphs identified the cause: offshore high pressure, pulling in warm air from the southwest. Subsequently, a heat advisory was announced for northeast New Jersey and the New York City metro area. But it was the next sentence that carried the most weight. The forecaster noted, "This is the first high heat index event of the year for northeast New Jersey and New York City." This simple statement is an operational admission that the public health risk is elevated. The advisory was issued not because an absolute temperature threshold was breached, but because the population was not yet prepared for this much heat, this quickly, so early in the season. This same thoughtful approach was mirrored by the Mount Holly office in their discussion. They wrote that this period of early season heat, with record-breaking temperatures likely, would have potentially greater impacts. That specific phrase is the language forecasters use to signal a critical shift in their assessment. It indicates that the public health variable, the fact that the population is not ready, has become the controlling factor in their decision to issue an advisory, even more so than the raw meteorological numbers. It is a quiet acknowledgement of the human element in a weather forecast. To understand the scale of this event, let's trace the movement of the air mass across the eastern seaboard. In central Virginia, the Baltimore-Washington office projected highs between 96 and 98 degrees for the Piedmont and the I-95 corridor. The atmospheric science behind this involves temperatures at the 850 millibar level, which were running between plus 19 and plus 23 degrees Celsius. When this air mixes down to the surface, it readily produces potential temperatures in the high 90s. With afternoon dew points in the upper 50s and low 60s, the air was dry enough that the heat index didn't soar far beyond the actual temperature. Still, it was uncomfortable enough to make any extended outdoor activity physically draining. The forecaster described it as another day of challenging record-high temperatures, noting that the forecast and the existing record for May 19th at Reagan National Airport were operationally indistinguishable. a technical way of saying the record would likely be tied or broken. Moving north into the Philadelphia metropolitan area, the Mount Holly office forecasted temperatures peaking in the 90s for many locations, with cooler conditions only along the coast and in higher terrain. A heat advisory was put in place for much of the region. Here, we see how warnings are tailored to specific environments. The office noted that while the general heat index criterion is 100 degrees Fahrenheit, the threshold for the urban I-95 corridor is lowered to 96 degrees through June. This adjustment accounts for the urban heat island effect and greater population density, which combine to increase the danger. The office projected peak heat indices between 95 and nearly 100 degrees. The advisory for areas farther north and west was set to expire sooner, as a cooler front was expected to bring relief to those locations first. However, buried within these forecasts was a detail far more concerning than the daytime highs. The office wrote that nighttime temperatures would be quite warm by mid-May standards, with lows only dropping into the mid-60s to low 70s. This, they noted, would challenge the daily warmest low temperature records for May 19th. It is a detail many might overlook, yet it points to the most insidious danger of a heat wave. The daily warmest low temperature record measures the highest minimum temperature observed over a 4-hour period. It quantifies how warm the night remained, and it is a profoundly important variable from a medical standpoint. The human body recovers from heat stress during the cooler hours of the night. When the overnight temperature fails to drop into the low 60s or 50s, that crucial recovery simply does not happen. The heat stress from the next day then accumulates on top of the previous day's unresolved stress. This cumulative burden disproportionately affects the most vulnerable among us: the elderly, the very young, those with cardiovascular or renal conditions, and the homeless. In the grim calculus of a heat event, the warmest low temperature record is the variable that often translates to the death count. And on May 19th and 20th, it was this very record that was being challenged all along the I-95 corridor. As we turn our attention northward, an unusual weather pattern is taking shape over New York City and northeastern New Jersey. Forecasts for today show temperatures climbing into the mid to upper 90 sets. While Brooklyn and Queens may experience slightly cooler highs, the overall heat indices will remain elevated. A relatively dry air mass is in place, with dew points holding in the low 60 sets. However, this is set to change with the arrival of a cold front on Wednesday afternoon. Ahead of this boundary, moisture will be drawn into the region, pushing dew points into the low to mid 60s. This interplay of heat and humidity is a delicate balance. Consequently, while Wednesday's high temperatures in the NYC metro are expected to dip into the lower 90s due to increasing cloud cover, the heat indices will persist in the mid-90s because of the added moisture in the air. Further north, a similar story of unseasonable warmth is unfolding across southern New England. The Boston Weather Office has noted that a heat advisory will remain active for much of the area on both Tuesday and Wednesday. This advisory, they explain, is not just due to a particularly oppressive combination of heat and humidity. Instead, it serves as a warning about the exceptionally early arrival of this level of heat, which is far from typical for mid-May. The temperatures at the 850 millibar level of the atmosphere, a key indicator for meteorologists, are projected to be between 18 and 20 degrees Celsius. These figures are 2 to 3 standard deviations above the climatological average, highlighting just how anomalous this event is. Here, local geography plays a crucial role. The warmest air will settle in the Connecticut and Merrimack valleys, where downslope winds could push temperatures into the mid-90s. In contrast, communities along the south coast will find relief as southwesterly winds blowing off the cool ocean surface act as a natural thermostat. with mid-May water temperatures still in the upper 50s to low 60s. This marine influence keeps the surface air mass significantly cooler. The sheer scale of this event becomes clear when we consider the population it affects. The heat advisory stretches across the entire I-95 corridor, encompassing a combined population of approximately 25 to 30 million people. Within this footprint lies New York City, with its metropolitan area of about 19 million residents. It also includes Philadelphia, home to around 6 million, and Boston, with roughly 4.5 million. Further south, the combined metro areas of Baltimore and Washington add another 10 million people to the count. The Connecticut and Merrimack valleys contribute an additional 2 million, while Central Virginia's Piedmont region adds another 4 million. This vast urban and suburban expanse represents the population center of the eastern United States, now simultaneously under a heat advisory. It is a moment that operational forecasters are describing as a record-setting early season heat wave. This intense and unseasonable heat places immense strain on the very systems that support this dense population center. The critical infrastructure, the electrical grid, the water supply, the public health network, and the transit systems will all be tested today and tomorrow. The first and most immediate stress variable is the electrical grid. When air conditioning demand suddenly jumps from a typical mid-May profile to one more characteristic of late July, regional transmission operators must scramble to find generating capacity that wasn't anticipated in their day-ahead market projections. For the PJM interconnection, which manages the grid for most of the I-95 corridor from northern New Jersey down through Virginia, this means reacting to sudden spikes in temperature forecasts from the National Weather Service. When these forecasts surge into record territory with only about 36 hours of notice, the day-ahead market is forced to find power sources outside the typical mid-May fuel mix. This chain reaction leads to natural gas peaking plants being called into service. As a result, spot prices in the wholesale electricity market climb sharply, and demand response programs, which pay large industrial and commercial users to cut back on their power consumption, are activated. While the grid is engineered to handle such high-demand days, and a blackout is not the expected outcome, the cumulative stress on the system is significant. The wear and tear on peaking plants increases, higher fuel costs are eventually passed on to consumers, and the risk of an unexpected failure at a major generation facility grows. The system is designed to bend, but each event adds to the strain. The pressure from this heat wave extends beyond the electrical grid and into the water flowing beneath the cities. As millions of people simultaneously increase their water usage for cooling, showering, and other activities, water utilities must push significantly more volume through their distribution systems. This presents a particular challenge for older cities like Boston, Philadelphia, and Baltimore, where aging infrastructure was not designed for the peak summer demands of a modern, fully air-conditioned populace. In some neighborhoods, especially those at higher elevations, the result can be a noticeable drop in water pressure. More critically, the added strain accelerates the stress on older water mains, occasionally leading to a break. It's a stark reminder of the hidden vulnerabilities that lie within our foundational infrastructure. Of all the systems under stress, the public health system bears the highest and most direct human cost. During a heat event affecting a population that is not yet acclimated to summer temperatures, emergency room admissions for heat-related illnesses invariably rise. Individuals with pre-existing cardiac and renal conditions, who may already be medically fragile, are more easily pushed into acute distress by the heat. The most vulnerable groups, the homeless, those without reliable access to air-conditioned spaces, and the elderly living alone in buildings without central air, are the ones who disproportionately appear in the mortality statistics that follow a heat wave. This is where the abstract numbers of a weather forecast translate into tangible human risk. The medical literature is unambiguous on this point. Studies comparing the public health impact of an early season heat event to a midsummer one with identical temperatures consistently find a higher mortality rate in the early season. The underlying mechanism is precisely the acclimation gap. Our bodies need time to adjust to heat, and this event has arrived before that process has begun. Today, across the I-95 corridor, the human cost of that gap is being measured in real time. As the heat continues into tomorrow, the gap widens further. The segment of the population that struggled to cope today will enter tomorrow already partially depleted, making them even more susceptible. This is why the 2-day heat advisory, issued by the New York City office to run from 11 a. Tuesday to 8 p.m. Wednesday, is so critical. It compresses 2 operational days into one continuous warning, acknowledging a grim reality. The public health risk does not reset to zero at midnight when the heat fails to relent overnight. And so, this is the story of the eastern half of the country, caught in the grip of an unseasonable and dangerous heat. While a vast heat dome settles over one part of the continent, affecting some 90 million people, a different but equally significant weather event is unfolding across the western and central regions. It is a powerful reminder of nature's balance, as the very same atmospheric physics that drive the intense heat are also fueling a corridor of severe storms stretching from Texas all the way to Vermont. This dual expression of energy reveals the intricate and interconnected dynamics of our atmosphere. The official forecast from the Storm Prediction Center, based in Norman, Oklahoma, captures the immensity of this event. Their convective outlook describes a slight risk of severe thunderstorms developing over a truly substantial portion of the nation. This zone of instability begins in west-central Texas, extends into the lower Mississippi Valley and the Mid-South, and then continues its journey northeastward through the Ohio Valley, across the lower Great Lakes, and into western and central New York. The language of meteorology, however, can sometimes understate the sheer scale of the phenomena it describes. To truly grasp what this forecast means, we need to translate its scope into more familiar terms. The corridor designated as a slight risk spans approximately 1.5 million square kilometers. On its southern end, it encompasses the sprawling metropolitan areas of Dallas-Fort Worth and Houston. It then sweeps over every major city in the Tennessee and Ohio valleys, including Memphis, Nashville, Louisville, Cincinnati, Indianapolis, Columbus, and Cleveland. Further north, the risk area covers the entire industrial belt from Detroit and Toledo to Buffalo, ultimately reaching the cities of upstate New York and Vermont. Within this enormous footprint reside an estimated 90 million Americans, all under the watch of this dynamic weather system. On the Storm Prediction Center's 5-tier scale, a slight risk is the second lowest category, which might suggest a relatively minor event. However, the operational significance of this forecast lies not in its intensity rating, but in its extraordinary geographic size. A slight risk that stretches from Dallas to Vermont is far from a quiet day for forecasters. This kind of broad footprint is typically issued when the atmospheric environment supports damaging weather over a wide area, rather than being concentrated into a single, high-risk corridor. It signals a widespread potential for disruption, a challenge of scale rather than localized severity. Across this vast expanse, the primary threats are expected to manifest differently depending on the region. For the Ohio Valley and the lower Great Lakes, the main concern is damaging winds. Operational forecasts anticipate that typical storm cells could produce gusts ranging from 45 to 65 miles per hour. The most intense cells, however, carry the potential for isolated gusts reaching between 70 and 75 miles per hour, strong enough to cause significant damage. This wind threat defines the northern leg of the severe weather corridor. Further south, in west-central Texas, the story and the underlying physics are entirely different. Here, the dominant threat is not wind, but hail. And this is not the small, dime to quarter-sized hail that might fall during a typical Texas spring afternoon. The forecast warns of discrete supercell thunderstorms capable of producing hail the size of baseballs, which form along a sagging cold front. This raises a serious concern for safety and property. Hail the size of a baseball measures roughly 2 3/4 inches in diameter. At this size, it is no longer a mere inconvenience, but a destructive force of nature. It can shatter windows, inflict widespread damage to vehicles, and cause serious injury to anyone caught outdoors without adequate shelter. The area of greatest risk in west-central Texas is centered on a corridor that runs from west of Abilene through the western portion of the Dallas-Fort Worth Metroplex and southward along the Interstate 35 corridor toward Waco. The atmospheric conditions fueling this specific hail signature represent a textbook setup for the formation of discrete supercells. A cold front is slowly drifting southeastward across the southern plains. Ahead of this boundary, a flow of moisture from the Gulf of Mexico is pushing surface dew points into the mid to upper 60 seconds. High above the surface, colder, mid-level temperatures are creating steep lapse rates, a rapid decrease in temperature with altitude, which translates into significant atmospheric instability once the afternoon sun heats the ground. This instability is measured by a value known as convective available potential energy, or CAPE. Forecasters expect mixed layer CAPE values to reach 1,500 to 2,000 joules per kilogram. This is more than enough energy to generate the powerful updrafts required to suspend and grow hailstones to baseball size. Adding to this volatile mix is the wind shear environment, which describes the variation of wind speed and direction with height. Across the axis of instability, effective bulk shear is predicted to be in the 35 to 45 knot range. This is the crucial element that allows storms to organize and rotate, transforming them into supercells with sustained updrafts that can persist for long periods. When you combine 2,000 joules of instability, Gulf moisture with dew points in the upper 60s, and 35 to 45 knots of shear, you have the precise recipe for the kind of storms that produce giant hail. The timing for these west-central Texas storms is anticipated for the mid to late afternoon, likely beginning between 3 and 5 p.m. Central Daylight Time. This is when the cap, a layer of stable air, is expected to break, allowing the first updrafts to surge through the lifting condensation level and into the unstable mid-troposphere. The storm cells will initially form as discrete units, separated from one another by tens of miles, with each one capable of generating its own signature of large hail. As these cells mature and climb higher through the late afternoon, the strongest among them will reach the altitude where they can sustain the growth of large hailstones, typically in the upper third of the storm column. The hail itself forms at altitudes of 7 to 9 kilometers above the ground, within a layer of supercooled water. It cycles through repeated upward and downward motions, allowing it to accumulate layers of ice until its weight finally overcomes the updraft's ability to support it, at which point it falls to the ground. As the afternoon progresses into evening, these powerful cells will be guided southeastward by the steering flow in the atmosphere. This means the hail threat will gradually shift from west of Abilene toward the I-35 corridor and the western side of the Dallas-Fort Worth area during the early to mid-evening hours. An important operational note from forecasters is that as these discrete cells mature, they are likely to merge and organize into what are known as bowing structures. This is the term for organized lines of thunderstorms that develop a coordinated outflow boundary, pushing them eastward as a single, unified system. These structures, known as a mesoscale convective system, or MCS, combine the initial hail signature with a new, significant threat of damaging winds. The MCS, expected to evolve from the discrete cells over west-central Texas, is forecast to continue its journey southeastward through the overnight hours. By the early morning on Wednesday, it is projected to reach south-central Texas, impacting the cities of San Antonio, Corpus Christi, and Houston. This overnight system will represent the second wave of severe weather to hit Texas in a single day. And it is this wave that will keep the alert ledger active across the southern plains well into the early morning. Meanwhile, far to the north in the Ohio Valley and lower Great Lakes, the storm mode remains different. The synoptic environment there supports organized convection, but it lacks the specific ingredients needed for the powerful, rotating supercells that define the Texas threat, illustrating how a single weather pattern can produce vastly different outcomes across a continent. The atmospheric shear present today is comparable in strength to recent events, but its orientation is less ideal for storm development along the primary boundary. While instability is also similar in magnitude, it is being unleashed by a different mesoscale force. This process involves the daytime heating of the ground beneath partly clear skies, working in tandem with convergence along an outflow boundary that has been moving eastward all morning. This complex interplay of factors shapes the day's potential for severe weather. The official forecast from the Storm Prediction Center anticipates scattered clusters of storms forming across the Ohio Valley and extending into western New York during the afternoon and early evening. The main danger from these systems is expected to be damaging wind gusts. The hail threat is generally limited to what is known as pocket change size, ranging from quarters to $half in diameter. However, isolated cells could produce larger stones if they manage to briefly organize their structure. It's important to note that while the tornado threat across the entire region is low today, it is not zero, and certain corridors warrant closer attention. The operational forecast identifies central Texas, within the discrete supercell environment, as one area where a brief spin-up tornado is plausible. Another zone of potential is the Lake Erie region, where lake breeze convergence can sometimes enhance low-level rotation in a storm that might not otherwise produce a tornado. A third area that may be added to later outlooks is central Indiana, where late afternoon storm development could become organized enough to support brief rotation. None of these areas, however, face the kind of high-end tornado threat that has defined the major outbreaks of recent weeks. In no meaningful sense is this a tornado day. The damage will instead come from wind and hail, with wind being the dominant force in the east and hail being the primary concern in the west. Through the morning, an extensive line of thunderstorms is already established, stretching from western Illinois southwestward into central Oklahoma. This line is generating damaging wind gusts between 40 and 60 miles per hour. These winds are mostly on a modest scale and are often embedded within heavy rainfall, which can mask the true wind threat from observers on the ground. This line of storms will continue its eastward march through the late morning and into the early afternoon. While it is expected to weaken somewhat during the daylight hours, it will maintain its signature of damaging winds as it moves across the Ozarks and into western Kentucky and Tennessee. Around lunchtime, the line will extend from Cape Girardeau, Missouri, back towards Dallas-Fort Worth. It is forecast to produce damaging wind gusts of around 60 miles per hour near the Metroplex, along with pocket-change-sized hail along its leading edge. By 2:00 to 3:00 inches the afternoon, the main line will be advancing across Arkansas, the Dallas-Fort Worth area, and the Texoma region. A new phase of weather will begin around 3:00 p.m. as the first discrete storm cells ignite west of Abilene. This marks the beginning of the significant hail signature for the day. As the mid-afternoon transitions into early evening, additional storms will develop across Michigan and Indiana, generally between 3:00 and 8:00 p.m. These storms are expected to be isolated to scattered in nature, carrying the potential for large hail and possibly a brief tornado if a single storm can fully mature in the environment. The main challenge for storm maturation in this region today is the sheer amount of potential convection within the same air mass. The storms effectively compete with one another for the available instability. This atmospheric battle means that most storms will likely remain disorganized and pose only a modest threat. Occasionally, however, a single dominant cell will emerge, growing into a more serious threat as it absorbs the instability from collapsing storms in its vicinity, a classic pattern for late afternoon springtime weather in the Ohio Valley. Between 4:00 and 5:00 inches the afternoon, the entire corridor is forecast to be active with high storm coverage. Near Detroit, storms will be capable of producing damaging wind gusts and possibly a brief tornado. Across central and northern Indiana, pop-up storms will attempt to do the same. A broken line of storms will stretch across Indianapolis and western Kentucky, bringing gusty winds. Farther south, storms throughout Arkansas, Louisiana, and East Texas will continue to push a damaging wind signature from Little Rock and Jonesboro down to Lufkin. Meanwhile, the discrete cells over West Texas will be producing the day's primary hail signature, with these storms beginning to organize into an early evening mesoscale convective system, MCS, that will track southeastward through the night. From 6:00 to 7:00 inches the evening, across the Ohio Valley, storm coverage near Fort Wayne and Indianapolis will be more scattered, though at times numerous. The primary concern here will remain the damaging wind threat, accompanied by a low tornado risk. By 9:00 to 10:00 p.m., most storms in the Ohio Valley will be weakening. This decline is due to the diminishing diurnal forcing as daytime heating fades and the re-establishment of the elevated mixed layer cap, which had suppressed convection earlier in the day. The severe corridor in the deep south, across Mississippi and central southern Louisiana, will likewise weaken through the evening, though it could still produce damaging winds up to 60 miles per hour. The only significant remaining concern for the overnight hours will be the South Texas MCS. This line of storms is expected to push through San Antonio, Corpus Christi, and Houston between approximately 2:00 and 6:00 a.m. on Wednesday morning. What some 90 million people are about to experience is not a tornado outbreak. Instead, it is a continental-scale severe weather pulse. This event will manifest as damaging winds in the Ohio Valley, giant hail in West Texas, and a sleepless night across South Texas as the late evening MCS moves through. The consequences of such a widespread event are significant. It will place immense pressure on the electrical grid as wind damage leads to scattered outages across multiple states at once. It will also strain the emergency response system as simultaneous severe weather events across numerous National Weather Service forecast areas stretch resources thin. This entire event sets the stage for the second act of the story. What happens on Wednesday when the cold front finally passes through and the entire pattern begins to unwind? If today represents the operational maximum of what this powerful Rossby wave is producing, then tomorrow will be its operational pivot, and Thursday will mark its operational collapse. The very same atmospheric wave responsible for today's heat dome and severe weather corridor is set to exit the stage over the next 48 hours. And as it departs, it will take the oppressive heat with it, bringing a dramatic close to this weather event. Across the eastern seaboard, a chorus of official forecasts is building toward a single, dramatic conclusion. The Baltimore-Washington office, in a discussion on the matter, anticipates a staggering 25 to 30 degrees nosedive by the end of the week. Farther north, the Boston office projects a Memorial Day weekend that is both cooler and unsettled, although they note that confidence in the precise details remains low. Forecasters in New York City are preparing for a much cooler air mass to settle in from Thursday through the holiday weekend, accompanied by chances of showers. Similarly, the Mount Holly office describes a cold front poised to bring widespread showers and thunderstorms on Wednesday, followed by a profound drop in temperature. Though originating from different locations, these forecasters are all interpreting the same atmospheric data and arriving at an identical conclusion. The atmosphere itself is about to flip. The engine driving this transformation is a powerful cold front, propelled southeastward by the same deep upper-level trough that has been lingering over the western United States. This atmospheric river of cold air is forecast to sweep through the mid-Atlantic region during Wednesday afternoon and evening. From there, it is expected to continue its journey across the southern New England coast through Wednesday night and into the early hours of Thursday morning. This progression sets the stage for a significant, if brief, period of atmospheric turmoil. The Storm Prediction Center's outlook for Wednesday anticipates a marginal to slight risk of severe weather. This threat extends from the Cumberland Plateau across the mid-Atlantic and into southern New England. The primary danger identified is damaging downburst winds, though isolated, marginally severe hail is also a possibility. To understand the storm's potential, we must look at the ingredients in the atmosphere. The discussion notes that ahead of the front, the air will hold between 1,000 and 2,000 joules per kilogram of convective available potential energy, the fuel for thunderstorms with minimal capping to suppress their growth. This environment supports a steady increase in thunderstorm coverage and intensity throughout the afternoon. However, the potential for highly organized, long-lived supercells appears limited. Forecasters note that the strongest vertical shear, a key ingredient for rotating storms, is located to the north of the surface warm sector. Yet, the presence of a well-mixed boundary layer, extending 1 to 1.5 kilometers deep, is highly supportive of locally damaging downburst winds developing through the afternoon and early evening. In short, the severe threat on Wednesday is certainly real, but it is not on the same continental scale as the events of the preceding days. The passage of the cold front will generate strong to severe storms, but they are expected to manifest as an organized line of cells along the boundary, not a sprawling corridor of destruction. While the tornado threat is low, the primary risks remain damaging winds and large hail, with a real but localized threat of flooding from slow-moving cells. This event will likely cause property damage, power outages, and travel disruptions, but it will not produce the kind of vast, multi-state severe weather signature seen earlier. What this system will produce, however, is a thermal collapse. Following the front, a completely different air mass will arrive, what the operational community refers to as Canadian air. This is a colder, drier air mass originating over the vast boreal forests and tundra of central and eastern Canada. While a late May cold front typically brings cooler air, the magnitude of this particular drop is noteworthy. The reason lies in the setup. The source region for this air is a high-latitude area that has not yet had a chance to warm for the season. Furthermore, the trough driving the front is amplified in such a way that it efficiently funnels this genuinely cold air southward. The result is a dramatic plunge in temperature. Afternoon high temperatures across the mid-Atlantic and New England are projected to fall from the mid to upper 90 seconds on Wednesday down to the upper 60 seconds and low 70 seconds by Thursday and Friday. This represents a drop of 25 to 30 degrees in just 24 to 48 hours. To put this in human terms, consider a person stepping outside in Philadelphia on Wednesday afternoon. At 3:00 p.m., they would feel air in the high 90s. If that same person were to step outside at the same time on Friday, they would be met with air in the high 60s. That is a 30-degree swing in the very variable our bodies use to calibrate nearly every decision, from clothing and fluid intake to outdoor activity, all within the span of 2 days, delivered by a single weather system. This abrupt reversal has profound implications. The population that just spent 2 days struggling to cope with mid-May heat in an unacclimated state will now spend the next 2 days adjusting back toward normal, but in the opposite direction, accompanied by rain, clouds, and the lingering humidity of a frontal passage. The entire rhythm of the region is set to reset. The power grid, which just handled a demand profile typical of late July, will suddenly see demand drop to late April levels. The peaking power plants that came online to meet the heat-driven demand will return to reserve status. Wholesale electricity prices that had spiked will fall, and water utilities that were running at high load will return to normal operations. In emergency rooms, the influx of heat-related cases will begin to taper off. Across 48 hours, the entire integrated system from public health and the workforce to the energy and water grids will undergo a complete reset. It is crucial to understand that this is not a normal frontal passage. A typical late May cold front in the mid-Atlantic might produce a 5 to 1 0-degree temperature drop and a noticeable, but not extreme, change in the weather. A 25 to 30-degree drop falls into the upper tail of possibilities for this time of year. Meteorologists attribute this to a high-amplitude wave configuration, a pattern where the prefrontal heat is exceptionally intense and the postfrontal Canadian air is unusually cool for late May, creating a larger than typical thermal contrast across the front. This rapid 30-degree swing, layered on top of a body that has just endured 2 days of unacclimated heat stress, is medically significant. The cardiovascular system, which spent 48 hours working overtime to pump blood to the skin for cooling, must suddenly readjust to a lower demand state. The body's metabolic systems, which were running in a heat stress mode, have to recalibrate. For most people, this transition is merely annoying and uncomfortable. But for at-risk populations, including the elderly and those with cardiovascular or renal compromises, this rapid reversal can act as a significant stressor in its own right. The medical literature on rapid temperature transitions identifies a smaller, but real, secondary cardiovascular risk in the days that follow a major heat event, especially when the subsequent cooling is this swift. Even the grid risk, though small, is worth noting in this period of dramatic atmospheric adjustment. The power grid is engineered to adjust to weather, scaling its output up or down as required. A dramatic temperature swing of 25 to 30 degrees, however, forces an extremely rapid transition that can place immense strain on individual generation facilities. This is especially true for peaking plants that have just been running at maximum capacity for 48 hours and must now be powered down. In the immediate aftermath, the risk of an unplanned outage at one of these plants is heightened. Though the regional transmission system is robust enough that this seldom becomes a public concern, a more subtle danger, however, emerges in the post-event fire weather risk. The dry, hot air on the western side of the cold front, combined with residual heat on the eastern side, leaves ground conditions significantly drier than before. Vegetation that has spent 2 days under heat stress, particularly the herbaceous fuels that respond quickly to deficits in atmospheric moisture, is far more combustible behind the front than it was ahead of it. If strong winds were to develop on the backside of the front, a scenario possible in a high-amplitude post-frontal regime, fire weather conditions could briefly worsen. The current forecast does not call for this in the mid-Atlantic, but the underlying dryness of the vegetation is a real consequence that will persist for days. Yet, what is forecast to follow this period of intensity is perhaps the most surprising part of this entire sequence. After Wednesday's cold front passes and temperatures plummet by 30 degrees, the synoptic environment is not expected to produce a follow-on event. There are no secondary fronts or sustained periods of severe weather on the horizon. Instead, the atmosphere is predicted to enter a period of extended quiet. For approximately a week, the conditions that generate major weather events will simply be absent. According to the operational forecast community, the next window for significant, organized, severe weather does not arrive for about 7 days. Forecasters are currently indicating that the next legitimate opportunity for such an event falls between May 25th and May 28th. This profound gap, this atmospheric silence, represents the second half of the story we are exploring, and it is a quiet that holds a deeper meaning. This behavior is not typical for the atmosphere. Ordinarily, an active period of weather lasting several days is followed by a brief transitional period, and then another active period begins. The pattern of a single, outsized event, succeeded by a week of calm, deviates sharply from this usual cycle. This is what the operational community refers to as a high-amplitude wave configuration. Such a configuration produces a compressed, multi-hazard event and then departs, leaving behind an environment depleted of the large-scale energy needed for organized weather to develop. The very wave that created today's extreme conditions is the same one that is now exiting, and crucially, there is no immediate replacement wave behind it. This is the fundamental rhythm that defines today's narrative: the intense maximum and the ensuing silence, the compressed pulse and the calibrated quiet. The Rossby wave that organized itself into this outsized event over the past several days peaked today, and it is now about to take its energy with it as it exits to the east. The critical question for the coming week, then, is what will come back to replace it? When you read the long-range discussions from operational forecasters, the answer is clear. A replacement wave is not visible in the model guidance for the May 20th through 24th window. The models instead show quiet. They indicate what is known as generally zonal flow, which is the operational term for a flat west-to-east pattern without significant wave amplification. While there may be scattered, weak, short waves moving through, there is nothing organized enough to produce a major, severe weather event. The synoptic environment, as forecasters describe it, is simply not very favorable. This operational forecast naturally raises a deeper question, one to hold in mind as we continue this exploration. Why does the atmosphere produce a 4-8-hour multi-hazard pulse only to then fall silent? What is the physical mechanism that can create such an outsized event followed by a calibrated period of quiet? And looking at the bigger picture, what might this unusual pattern tell us about what the same atmosphere will do in the coming weeks and months? This question becomes even more pressing as the El Niño Southern Oscillation Index continues its slow drift from neutral into watch territory, suggesting the synoptic environment will become more energetically forced by a developing El Niño backdrop. The answers to these questions are found in the physics we are about to explore. To begin unpacking these physics, we must first understand how a single atmospheric wave can present two such different faces. To truly grasp why today's weather is unfolding as it is, we must look at something called a Rossby wave. It is essential, however, to understand this not as a piece of obscure meteorological jargon, but as a real, physical object. This object possesses distinct properties, a shape, a phase, and an amplitude, and it affects the air beneath it in specific ways, all depending on how those properties are configured. A Rossby wave is a long, slow, large amplitude oscillation in the mid-latitude westerly flow of the atmosphere. These waves are named after the Swedish-American meteorologist Carl Gustaf Rossby, who, in the 1930s, worked out the physics connecting the rotation of our planet, the temperature gradient from the equator to the poles, and the apparent meandering of the jet stream into a single mathematical framework. In essence, these waves exist because the planet rotates and because the equator is warmer than the poles. This combination sets up a circulation that, when viewed on a global scale, organizes itself into a series of waves. These waves propagate slowly eastward around the mid-latitudes, with typically 5 to 7 complete wavelengths encircling the entire hemisphere. The character of our weather is profoundly influenced by the amplitude of these waves. When they are in a low amplitude state, the jet stream appears relatively flat on a map, running mostly west to east, with only shallow meanders. The weather systems beneath this pattern are generally fast-moving, progressing eastward at 30 to 50 miles per hour. For any single location, this means a typical weather cycle lasts only a day or two before the next system arrives. In contrast, when the waves are at high amplitude, the jet stream looks deeply meandering on a map, with deep troughs and tall ridges. It is this high amplitude state that sets the stage for more extreme and prolonged weather events. When an atmospheric pattern has a high amplitude, its movement tends to be more deliberate. Weather systems progress eastward at a slower pace, leading to weather cycles at a given location that can last from 3 to 5 days or even longer. This is the very mechanism that creates persistent weather, a kind of atmospheric lock where a region experiences the same conditions day after day. What we are witnessing today is a high-amplitude wave pattern captured in a specific phase. A deep trough is currently positioned over the western United States, while a powerful ridge dominates the southeastern U.S. and the western Atlantic. The distance between the trough's axis and the ridge's axis, its wavelength, stretches roughly from the Rocky Mountains to the Atlantic coast. This single wave is producing two distinctly different, yet physically connected, outcomes for the air beneath it. On the western side of this formation, under the influence of the trough, the air is being lifted. The wave generates a powerful rising motion, which cools the air as it ascends. This cooling process forces any water vapor present to condense, forming clouds and eventually precipitation. The trough is also responsible for drawing cooler air southward from the north. This explains the cool weather that has lingered across the Pacific Northwest and the Intermountain West for several days, as well as the recent late-season snowstorms in Wyoming and Colorado. The cold front now sagging across the plains represents the distinct boundary between this southward-flowing cool air and the warm air held in place to the east by the ridge. It is along this very boundary, in the warm sector, where today's severe weather is erupting, as moist Gulf air collides with the advancing cold front, destabilizing the atmosphere and triggering convection. Meanwhile, on the eastern side of the wave, beneath the ridge, the air is being suppressed. The wave induces a sinking motion, a process known as subsidence. As this air descends, it warms through the same dry adiabatic mechanism that governs temperatures at the 850 millibar level. This sinking motion also dries the air, because the warming effect reduces the relative humidity of any moisture it contains. Furthermore, the ridge facilitates the northward transport of warmer air from the south. This is the origin of the warm, humid air mass from the Gulf and the Atlantic that currently blankets the I-95 corridor. The heat dome we see today is the direct result of the ridge performing its fundamental functions, suppressing vertical motion, warming the air column, drying the atmosphere, and importing warmth from the south. The combination of these factors is what produces the surface temperatures we are observing. So, the basic physics become clear. A trough can generate severe weather on its eastern flank, while a ridge can produce a heat dome at its center. The amplitude of the wave dictates the intensity and persistence of both of these signatures. The crucial insight is that these two phenomena are not mere coincidences. They are physically linked, produced by the same wave at the same time. They are, in essence, the two operational faces of a single, underlying atmospheric configuration. The next question, then, is a profound one. Why is this wave exhibiting such a high amplitude at this specific point on the calendar? It is here that the peer-reviewed scientific literature becomes especially compelling. A growing body of research in atmospheric science, building since the late 2010s, has focused on whether the frequency of high-amplitude wave configurations, like today's, has changed over recent decades, and if so, what might be causing it. A leading figure in this field is the German atmospheric scientist Kai Kornhuber. His work, first published in Nature Climate Change in 2020, and later updated in Nature Communications in 2023, identifies a particular class of high-amplitude wave known as a wave number 5 to 7 quasi-resonant amplification event. While the technical term may seem dense, its meaning reveals a great deal about our planet's changing climate system. Let's unpack what this term signifies. The wave number 5 to 7 refers to the number of full wavelengths, each comprising one ridge and one trough that encircle the hemisphere. A wave number 5 pattern, for instance, means there are 5 distinct ridges and 5 troughs wrapping around the planet's mid-latitudes. Similarly, a wave number 7 pattern has 7 of each. These are planetary scale waves, shaping weather across entire continents. The quasi-resonant part of the name describes a phenomenon where the wave, instead of propagating eastward at its usual speed, becomes stalled in place for an extended period. The atmosphere has natural frequencies at which it prefers to oscillate. When an external force, such as the temperature gradient between the rapidly warming Arctic and the consistently warm tropics, drives the atmosphere at a frequency close to one of these natural resonances, the wave's amplitude can be greatly amplified, and its eastward movement can slow to a crawl. The result is a weather pattern that becomes locked in. The same ridge and the same trough can remain over the same locations for days or even weeks, rather than moving on. When such an event occurs during the summer months in the Northern Hemisphere, the consequences can be severe. The same regions are subjected to the same weather patterns repeatedly. A stationary ridge sitting over a continent can produce a sustained and intense heat dome. At the same time, a stationary trough over another region can lead to prolonged periods of severe weather and flooding. Because the wave itself is global, not local, this configuration can synchronize extreme weather events across multiple geographic regions simultaneously. A wave number 5 amplification event, for example, can produce simultaneous heat extremes across North America, Europe, and Central Asia, as the ridges of the wave all reach their peak intensity over their respective continents at the same time. In their 2020 paper, Kornhuber and his collaborators discovered that during these quasi-resonant wave number 5 and 7 events, the probability of concurrent heat extremes across multiple major agricultural regions is enhanced by a factor of up to 20 compared to non-resonant periods. The paper also found that the probability of regional crop loss increases by an average of 4% globally and by as much as 11% regionally during these resonant amplification events. This represents a substantial and concerning signal in the data. The research was the first to assign precise statistical weight to something operational meteorologists had been observing for years, that the major heat events of the 2010s and beyond all seemed to share a common, underlying signature. The European heat domes of 2018 and 2019, the Pacific Northwest Dome of 2021, and the Texas Dome of 2022 all showed evidence in the upper-level wave field that pointed toward amplified resonance as the fundamental physical driver. A 2023 follow-up paper in Nature Communications revealed a finding with profound operational significance for the events we are witnessing today. The study found that our current generation of climate models consistently underestimates the observed frequency of synchronized, concurrent extremes. In other words, the real-world atmosphere is generating these compressed, multi-hazard events more often than our best predictive tools anticipate. This underprediction isn't a minor error. It is statistically robust across numerous model families. While the paper does not yet offer a fully confirmed physical reason for this discrepancy, it proposes several compelling candidate mechanisms. These include how models represent the Arctic temperature anomaly, their handling of ocean heat content in the North Atlantic, and the complex coupling with soil moisture, a topic we will explore later. The immediate takeaway is that whatever process is driving wave amplification in the atmosphere, It is unfolding faster than the models suggest it should. This scientific literature provides the essential context for today's atmospheric behavior. The current event is operationally consistent with a quasi-resonant amplification of wave numbers 5 to 7. We are observing a high-amplitude wave, with its ridge and trough both firmly anchored in place. The timing of this setup is producing a compressed, multi-hazard event, precisely the kind of configuration that Kornhaber and colleagues have described as occurring with increasing frequency beyond what models would predict. As we have explored in detail on Calm Space in recent days, including our video from May 16th, this framework offers a powerful lens for understanding the current pattern. What is new today is not the theory itself, but its stark manifestation. Today represents the operational verification of what the framework predicts. A compressed event featuring simultaneous heat, severe weather, and flooding across a vast continental scale. The synchronization of these two faces of the wave, the intense heat and the violent storms on the very same day, is exactly the operational fingerprint that the scientific literature describes. This alone would be significant, but the timing adds another layer of gravity. The fact that this is all unfolding on May 19th, a calendar date when such an event is statistically least likely, according to the empirical record, is deeply concerning. This is precisely the scenario the literature warns is now happening more often than our models have been programmed to expect. It raises a fundamental question about whether our historical understanding of seasonality can keep pace with a changing climate. So, what is the underlying cause? The wave has achieved such a high amplitude because the atmosphere is currently in a configuration that supports the amplification of wave numbers 5 to 7. This amplification, in turn, is the direct cause of today's compressed multi-hazard event. The compression is occurring earlier in the calendar season than the historical baseline suggests it should. The underlying drivers, including accelerated Arctic warming, shifts in the equator to pole temperature gradient, anomalies in ocean heat content, and soil moisture coupling, are all leading candidates for why the frequency of these powerful events appears to be on the rise. Now we arrive at the part of the story that is not yet being widely discussed, and it is arguably the most operationally interesting. After the passage of a cold front on Wednesday, which will bring a dramatic 25 to 30 degree temperature crash, the synoptic environment across the eastern United States is not expected to produce another organized event. Instead, it is forecast to go quiet. According to the operational forecast community, the next significant window for organized severe weather will not arrive for approximately a week, with the next legitimate chance for a comparable multi-hazard event identified around May 25th through May 28th. This is a profound departure from a normal forecast cycle. A typical late May pattern in the United States involves an active period of 3 to 5 days, followed by a transitional day or two, and then the start of another active period. The projected pattern of one single, outsized day followed by nearly a week of synoptic scale silence is not normal. It is the signature of an exhausted atmosphere. This is the kind of pattern that often follows a quasi-resonant amplification event. Once the wave that produced the extreme weather finally exits its configuration, the atmosphere must spend several days reorganizing itself before it can generate another high-amplitude wave somewhere else. The physical mechanism behind this post-event quiet is a fascinating process of energy depletion, which was touched upon in a 2021 paper by Han in Water Resources Research. A high-amplitude wave that becomes stuck in place effectively draws energy from the surrounding flow. This energy is sourced from the temperature gradient between the warm and cold sectors, and from the kinetic energy of the jet stream the wave is embedded within. As the wave persists for days, it depletes this local energy reservoir. When the wave finally breaks down or moves on, the atmosphere it leaves behind is sapped of the synoptic scale energy needed for another high-amplitude wave to form quickly in the same region. The result is a quiet period that can last for several days to a week, until the surrounding flow reorganizes and a new energy gradient is established. The forecast for the May 20th through 24th window shows exactly the kind of quiet one would expect from this post-amplification depletion. The atmospheric flow is projected to shift from the high-amplitude wave configuration toward a more zonal pattern. A zonal pattern, the operational term for a flatter, west-to-east jet stream with only shallow meanders, does not support the conditions necessary for major weather events. It cannot sustain strong surface frontal development, powerful vertical motion, or the kind of large-scale moisture transport that fuels severe weather and flooding. In the precise language of forecasters, the synoptic environment becomes not very favorable for organized severe weather. The sequence is therefore clear. The atmosphere produces today's major event, followed by Wednesday's cold front and temperature crash, and then enters a synoptically depleted state that persists for roughly a week. The next time the system can produce an organized event is when the next high-amplitude wave reorganizes, which is forecast for approximately May 25th through 28th, as a new troughing ejection over the Rockies sets up the next configuration. What is most interesting about this, from an analytical perspective, is what the silence implies. This quiet period is not the absence of weather. It is the absence of times organized times weather, a subtle but critical distinction that speaks volumes about the immense energy expended in a single, amplified day. Across the United States, the period from May 20th through the 24th is forecast to bring a relative lull, while scattered showers and thunderstorms will persist, marking the daily rhythm of weather variability. The atmosphere will be without the kind of multi-hazard pulse recently experienced. There will be no widespread severe weather outbreak, nor a continental-scale frontal passage capable of dropping temperatures by 30 degrees. In a sense, the atmosphere will be taking a breath for about a week. This quiet interlude is operationally significant, as it allows the atmosphere to rebuild its reservoir of energy, setting the stage for the next major event forecast to arrive around the Memorial Day weekend. That upcoming window, from May 25th through the 28th, carries unusual weight for several reasons. It coincides with the Memorial Day weekend in the United States, a time when millions of people are traveling or attending outdoor gatherings, placing them in positions where weather disruptions can have exceptionally large social consequences. For the aviation industry, this marks the beginning of the operational summer, meaning any organized severe weather could trigger a cascade of flight disruptions throughout the national air travel system. Furthermore, this period is scheduled to host major outdoor sporting events, including the Coca-Cola 600 at Charlotte Motor Speedway and the Indianapolis 500 at the Indianapolis Motor Speedway, both highly vulnerable to weather-related disruption. At the same time, the agricultural sector across the central U.S. will be in a critical phase of late planting and early vegetative growth for corn and soybeans, amplifying the potential for crop damage from any hail or high wind events. As of now, the operational forecast community cannot say with certainty what the event between May 25th and 28th will entail. The model guidance at this range is simply too uncertain for confident predictions about specific severe weather threats. However, forecasters are closely monitoring the broader synoptic environment, particularly the formation of the next high-amplitude wave configuration. The nature of this configuration is critical, as its arrival will likely serve as the next major operational test of whether the recent, persistent run of powerful amplification events is set to continue. It raises a fundamental question. Are we witnessing a temporary anomaly or a new, sustained atmospheric pattern? What might surprise many is just how continuous this series of high-amplitude events has been over the past several weeks. The mid-April outbreak, which spawned an EF4 tornado in Enid, Oklahoma, and an EF3 in Mineral Wells, Texas, was one such event. The bicoastal heat dome on May 8th was another, followed by its inland migration on May 9th. Even the M5.7 solar flare from active region 4436 on May 10th, while a space weather phenomenon occurred against the same large-scale atmospheric backdrop. The severe U.S. drought signal on May 12th was the cumulative downstream result of a sustained high-amplitude pattern that had suppressed rainfall for months. This was followed by a multi-day severe weather sequence on May 13th and a fire weather corridor on May 16th. The convergence on May 18th, a Wyoming blizzard, and an East Coast heat dome rebuild on the same day, was the most extreme example in the sequence, with May 19th serving as the operational verification and the single highest magnitude event in this recent run. If the upcoming May 25 to 28 window delivers another event of comparable scale, it would strongly suggest that the pattern of the last few weeks is no coincidence. Instead, it would point to a sustained high-amplitude regime, a state that produces powerful events one after another, with only brief synoptic scale recoveries in between. The scientific literature suggests that such a regime tends to persist until a larger force intervenes to change it. On a timescale of weeks to months, that change could come from the ENSO state. Over months to years, it could be driven by longer-term climate forcings, such as Arctic warming and shifts in ocean heat content that reshape the very temperature gradients on which wave amplification depends. Since neither of these factors is expected to change between now and the end of May, the private consensus among forecasters is an expectation that the high-amplitude regime will continue. This leads to a crucial question. After the maximum, after the crash, and after the subsequent silence, what comes back? The answer emerging from the operational community is that the silence is only temporary. The recovery is structural, and the next event is already developing on schedule. The atmosphere appears to be locked in a regime, and this regime is what generates the events. Today, May 19th, is a powerful manifestation of this pattern. The period from May 25th to 28th will likely be another. The pattern, it seems, is set to continue. But to fully grasp the magnitude of these events, we must look beyond the atmosphere to the ground conditions below. The heat dome, currently affecting 90 million people, is not merely the product of an atmospheric wave. It is a heat dome formed by a wave that is sitting atop a continent gripped by the most severe drought ever recorded in the modern instrumental era. It is the dangerous interplay between these two variables, the atmospheric disturbance and the parched land, that is producing the intensity of the event we are witnessing. The immense heat dome under which 90 million people are currently situated is not developing over a normal landscape. It is unfolding over a continent that, according to formal measurements from the National Centers for Environmental Information, is experiencing its worst spring drought conditions in the entire modern instrumental record. This critical context was explored in detail in a Calm Space feature from May 12th, which focused on the historic nature of this drought. We will summarize the key points here, as this background is essential for understanding the severity of today's weather, without needing to relitigate what has already been covered. The data provides a stark picture of this underlying condition. For the lower 48 United States, the Palmer Drought Severity Index for March 2024 registered at negative 7.85, calculated against the 1900 to 2024 baseline used by the National Centers for Environmental Information. The value for April was negative 7.56. These figures represent the most negative monthly values the index has produced since the Dust Bowl years of 1934. This is the statistical reality of the loaded ground that is amplifying every atmospheric event that passes over it. The early months of 2026 painted a concerning picture across the contiguous United States. The cumulative precipitation from January through March was the lowest recorded since data collection began in 1910, and the period extending through April was the second lowest. This dryness was especially acute in the southeast, where the climate region, including the Atlantic coastal states, endured its most arid April in 4 decades. For 6 of these states, it was one of the 10 driest Aprils in their entire climatic history. These are not just abstract statistics. They represent a landscape steadily losing its resilience. By late April, the U.S. Drought Monitor revealed that approximately 44% of the lower 48 states were in the grip of D2 severe drought, or worse, a geographic footprint larger than any seen since August of 2012. Within the southeast, an astonishing 99% of the land was experiencing drought, with 61.2% classified under the most dire categories of D3 extreme or D4 exceptional. In Florida, the statewide drought intensity reached the highest level ever documented. This is the parched, thirsty ground upon which today's formidable heat dome now sits. The connection between this profound dryness and the intense heat is not a coincidence, but a matter of physics. A 2019 paper by Morales, published in the Proceedings of the National Academy of Sciences, identifies a crucial coupling mechanism between soil moisture and the atmosphere. The research found that when the moisture in the underlying soil falls into the lowest 10th percentile of its historical range, the probability of an extreme heat event increases by approximately 30%. The process itself is straightforward. Normally, the ground cools the air above it through a process called evapotranspiration, where water evaporates from the soil and transpires from plants. But when the ground is exceptionally dry, this natural cooling system effectively shuts down. As a heat event begins, the air warms without this moderating influence, which in turn dries the soil even further. This creates a powerful feedback loop, where escalating heat and increasing dryness amplify one another, pushing temperatures ever higher. What this means is that the heat dome, currently centered over the I-95 corridor, is more than a simple atmospheric phenomenon. It is a compound event, powerfully intensified by a soil moisture deficit that is itself at the extreme end of the historical record. The temperatures soaring over millions of people are significantly higher than they would otherwise be, precisely because the ground beneath them is so profoundly dry. This is the dry soil amplification mechanism detailed in the Morales paper, a principle that operational forecasters quietly recognize. When they observe temperature anomalies that far exceed what atmospheric patterns alone can explain, they understand that a powerful force from the ground up is contributing to the extremity of the event. It is a silent amplifier, turning a significant heat wave into a historic one. To understand the full context of this dryness, we must look further back in time. A landmark 2022 paper by Williams, published in Times Nature Climate Change, used a network of tree rings to place the ongoing southwestern megadrought into a 1,200-year perspective, with data reaching back to 800 CE. The study's findings were stark. The two-year period from 2000 to 2021 was the driest such interval the American Southwest has experienced in at least 12 centuries. Critically, the paper attributed 42% of the soil moisture deficit during this megadrought directly to anthropogenic forcing. This suggests that without the influence of human-caused climate change, the drought would have been substantially less severe, perhaps remaining within the bounds of natural variability. This research forges a direct link between long-term climate trends and the immediate crisis. This chain of attribution has only grown stronger. Updated analysis from CU Boulder in 2025 extended the research through the most recent years, finding that the human contribution to the drought has not diminished. If anything, as global warming has continued, the anthropogenic share of the cumulative soil moisture deficit has continued to grow. When we combine the findings of the Williams megadrought attribution with the Morales dry soil amplification mechanism, a clear and disturbing causal chain emerges. It runs from anthropogenic forcing to a historically severe soil moisture deficit, and finally to the dangerous amplification of heat. This is not a theoretical model for the future. It is a chain of events actively unfolding right now, directly beneath the I-95 corridor. The heat dome, under which 90 million people are living, is in part a downstream consequence of this interconnected system. A megadrought, intensified by climate forcing in the southwest, has contributed to a broader continental drought signature. This widespread dryness is now amplifying a synoptic-scale heat event in a geographically separate region. It serves as a powerful illustration of how climate disruptions in one area can have profound and unexpected impacts thousands of miles away, tying the fate of disparate regions together. The arid landscape of the West is directly contributing to the oppressive heat felt on the East Coast. Yet, this story has another dimension, a third face of the same vast atmospheric wave pattern: widespread flooding. While one part of the country bakes, another is inundated. As of today, the National Weather Service has 59 active flood warnings across the central United States. The most significant impacts are being felt along the White River system in Indiana, the Grand River system in Missouri, and the Calcasieu and Vermilion River systems in Louisiana. These floods represent a separate operational challenge, affecting different populations with their own distinct set of consequences, yet they are born from the very same atmospheric setup. The details from weather offices on the ground reveal the scale of the threat. In Indiana, the Indianapolis Forecast Office has issued extended flood warnings for communities like Elliston, Newbury, Edwardsport, and Petersburg, with some alerts projected to last through May 29th. To the west, the Kansas City office has issued similar long-duration warnings for towns along the Grand River, including Gallatin, Sumner, Chillicothe, and Brunswick, some extending through May 24th. Further south, the Lake Charles office is monitoring flooding on the Calcasieu and Vermilion rivers, with warnings active through the weekend. Each warning represents a community facing the threat of rising waters. In Texas, the Houston-Galveston office described a persistently wet and muggy weather pattern in its 6:30 a.m. discussion this morning. The amount of moisture in the atmosphere, known as precipitable water, is near 2 inches, a value well above the 75th percentile for this time of year. Forecasters anticipate multiple rounds of storms capable of producing rain at rates of 3 to 4 inches per hour. The office noted that long-range guidance points toward this wet trend continuing, with 5 to 7 inches of total rainfall likely over the next 7 days. The forecaster explicitly stated that the issuance of a flood watch for the upcoming Friday could not be ruled out, signaling a high potential for more widespread flooding. Even far to the north, in Alaska, this continental pattern is making its presence felt. The lower Yukon Valley is under a flood warning at Holy Cross, where the release of the Yuki ice jam is causing high water and ongoing flooding. While ice jam flooding is an annual concern during the spring thaw, this particular event is causing rivers, creeks, and other low-lying areas to overflow their banks, with a warning in effect until 10:00 inches the evening, Alaska Daylight Time. It's a reminder of the immense geographic scale of these interconnected weather systems. Including this story of flooding is essential because it is not a separate event, but rather the third expression of the same Rossby wave configuration that is driving the heat. The very same trough of low pressure over the western United States, which is helping to build the heat dome in the east, is also responsible for pulling a deep flow of moisture from the Gulf of Mexico across the southern plains and into the nation's heartland. This atmospheric river is the mechanism feeding the storms and fueling the floods. It is a profound paradox of our modern climate, a single atmospheric pattern, delivering two entirely different forms of disaster to a continent. The same atmospheric wave generating the eastern heat dome and the central severe weather corridor is also the source of the flood signature across the central and southern regions. It is a single weather pattern, manifesting in three distinct ways. Of these, the flood story is the one that unfolds most gradually, developing over days and weeks rather than a single afternoon. Yet, this slow-moving disaster is often the one that results in the greatest cumulative property damage and demands the longest and most arduous recovery. This very process is currently underway, impacting multiple states simultaneously. When we look at the full picture, we see the interplay of heat, severe weather, and floods, all stemming from one wave configuration. This entire system is superimposed upon the most severe drought conditions in the modern instrumental record, amplifying its effects. The result is a continental-scale event with several expressions happening at once. The term that the operational community is using to describe this, a compressed multi-hazard pulse, feels not just accurate, but essential. It captures the complex and overlapping nature of the challenges at hand. Before we continue, there is one more element of the underlying physical context that must be addressed. It is a real and actively debated area within the scientific literature, and a thorough examination requires an honest look at this controversy. The issue centers on the question of accelerated warming observed since 2020, particularly over the North Atlantic and Western Pacific. Scientists are exploring whether this acceleration and the apparent increase in high-amplitude wave events that followed is partially driven by the removal of marine sulfate aerosols. This change was a direct result of the International Maritime Organization's 2020 sulfur cap on shipping fuel. The story begins on the 1st of January 2020, when the International Maritime Organization enacted a new global regulation. This rule dramatically lowered the maximum allowable sulfur content in marine fuel from 3.5% down to just 0.5%. The primary goal was to improve public health and reduce acid rain by cutting sulfur dioxide emissions from the shipping industry. And in this, it was a resounding success. Global sulfur dioxide emissions from shipping plummeted by an estimated 75% to 80% in the following years. However, some atmospheric scientists had warned of an unintended consequence. The sulfate aerosols produced by those emissions had been acting as a kind of planetary sunshade, reflecting a portion of incoming solar radiation back into space. This provided a small but significant cooling effect that partially masked the full extent of underlying greenhouse warming. With the aerosols suddenly removed, this masking effect vanished, exposing the true level of accumulated heat. According to one school of thought, this unmasking triggered an acceleration in the rate of planetary warming. The effect was most pronounced over the North Atlantic and Western Pacific, the very regions with the highest density of shipping traffic, and thus the largest prior aerosol concentration. The most prominent scientist advancing this position is James Hansen, the former NASA climate scientist. In a 2023 paper published in Earth and Environment, he explicitly attributed an additional 0.05 degrees Celsius of warming acceleration per decade to this post-2020 aerosol unmasking. Hansen's paper has been widely cited and has become a leading candidate explanation within the broader climate research community for the extraordinary temperature spikes observed in 2023 and 2024. This acceleration is not a matter of debate. It is a real phenomenon documented in multiple independent temperature records, including those from Copernicus, NASA GIS, and the Hadley Center. However, a counter-argument, published by Quaglia and Visioni in Atmospheric Chemistry and Physics in 2025, offers a different perspective. It suggests that while the aerosol unmasking effect is real, its magnitude is smaller than what Hansen and his colleagues have proposed. The Quaglia and Visioni paper places the post-2020 aerosol contribution to warming acceleration at a much lower value, closer to 0.01 to 0.02 degrees per decade. They argue that the remainder of the observed acceleration can be attributed to other forces. These include the continued accumulation of greenhouse gases, natural climate variability linked to the recent El Niño event, and changes in ocean heat content that are not solely caused by the aerosol unmasking. It is crucial to understand that the Quaglia and Visioni paper is not a dismissal of the Hansen hypothesis. Rather, it is a scientific refinement, positioning the effect's magnitude at the lower end of the plausible range. The honest scientific framing is that this is an active and important debate. The aerosol unmasking hypothesis is plausible, and the evidence for some effect is reasonably strong, but its precise magnitude remains contested. Where this scientific debate becomes relevant to today's event is in the question of causation. Could the apparent recent increase in high-amplitude wave amplification events be driven, in part, by this aerosol unmasking? If the unmasking is causing additional warming over the North Atlantic, the resulting changes to the temperature gradient between the ocean and the surrounding continents could be fostering the very conditions that favor this type of quasi-resonant wave amplification. This potential chain of causation is something the literature has not yet fully resolved. The Kornhuber papers identify the increased frequency of these waves, and Hansen's paper offers a candidate forcing mechanism to explain it. The link between the two is plausible, but it has not been definitively established. A position of scientific restraint would conclude that today's weather event is not, in any direct and meaningful sense, caused by the aerosol unmasking. The synoptic configuration producing the current conditions is the high-amplitude wave. That wave is being driven by the temperature gradient between warm and cold sectors and by the ocean heat content of the surrounding basins. The aerosol unmasking is simply one of several candidate explanations for why these powerful wave events seem to be occurring more frequently. It is a possible contributing factor to a long-term trend, not the direct cause of any single event, including this one. The cause of today's event is the wave, and that wave is being amplified by a configuration of underlying drivers that include soil moisture deficits, Arctic temperature anomalies, ocean heat content, and possibly the aerosol unmasking, all working in concert. This is the kind of honest, multifaceted framing we should apply to all contributing factors. No single mechanism is the sole explanation. Instead, multiple reinforcing factors are operationally relevant, with the atmospheric wave acting as the proximate cause of the events we see unfolding on the ground. The long-term environmental picture is a complex one, woven from threads of drought, warming trends, shifting gradients, aerosols, and the trajectory of ENSO. These elements interact in ways that science is still actively working to understand. Rather than offering a simple, single-cause narrative, which headlines often favor, the honest version embraces this intricacy. It is this more complete and nuanced story that Calm Space is dedicated to exploring. To place today's atmospheric developments in their proper context, we will now take a brief tour of the rest of our planet, observing the key operational signals across other global systems. This survey helps create a complete picture of this moment in time. It also serves to underscore the unusual nature of today's primary story by highlighting what is, by contrast, proceeding as expected elsewhere. On the geological front, the United States Geological Survey has logged 84 earthquakes of magnitude 4.5 or greater around the world in the past 7 days. The largest of these in the last 24 hours was a magnitude 5.7 tremor in Vanuatu, occurring at a depth of 27 kilometers, approximately 51 kilometers southwest of Port Vila. The USGS issued a green alert, indicating that no significant casualties or economic losses are anticipated. Roughly 3 hours later, a magnitude 4.8 aftershock was recorded 13 kilometers southwest of the same town. Other seismic events of note included a magnitude 5.4 quake on the West Chile Rise, a 5.3 inches the Bouvet Island region, and several magnitude 5.2 events on the Mid-Indian Ridge, in China's Guangxi province, and in Burma. An unusual pairing of deep focus earthquakes south of the Fiji Islands, with magnitudes of 4.6 at depths of 589.8 and 564.7 kilometers, occurred within 24 hours of each other. While this Fiji pairing is a noteworthy signature, the overall global seismic activity remains within the normal range for a one-week interval. Turning to volcanic activity, 4 volcanoes in the United States currently carry elevated alert levels. Great Sitkin in the Aleutian Islands is at a watch status with an orange aviation color code. Meanwhile, Kupayanaha, Shishaldin, and Kilauea are all at an advisory level with yellow aviation codes. The Yellowstone Volcano Observatory's latest report also identified 5 minor hydrothermal explosions so far this year at Black Diamond Pool, with the most recent occurring on April 28th. The observatory points out that the webcam monitoring this pool is mounted on what remains of a boardwalk destroyed by a larger explosion at the same site on the 23rd of July 2024. While 5 explosions at a single feature is above its baseline and warrants continued monitoring, this activity does not approach the operational significance of what is currently unfolding in the atmosphere. Looking outward from our planet, the space weather environment remains relatively calm. The coronal mass ejection from May 16th, which produced a G2 geomagnetic storm last week, is now delivering only a glancing blow to Earth. Over the past 24 hours, the highest observed 3-hour planetary K-index was 4, which is just below the threshold for a NOAA G1 storm. The forecast through May 21st anticipates a peak K-index of 4.67, which would technically qualify as a G1 event. Solar wind speeds are declining, measuring 526 kilometers per second this afternoon. The largest solar flare in the last day was a modest C2, one from active region 4,436. Of the 4 numbered active regions on the visible solar disk, only region 4,441 shows moderate complexity, with a 25% chance of a class flare and only a 1% chance of an X-class flare in the next 24 hours. With no Earth-directed CMEs in current imagery, the space weather environment is expected to stay quiet through May 21st. Meanwhile, humanity's own endeavors in space continue to advance. The European Space Agency's Solar Wind, Magnetosphere, Ionosphere Link Explorer mission, known as SMILE, launched successfully at 3:52 a.m. Coordinated Universal Time. The joint mission between ESA and the Chinese Academy of Sciences will, for the first time, image the global-scale interaction between the solar wind and Earth's magnetosphere, using advanced X-ray and ultraviolet images. Its unique elliptical orbit will allow it to spend long periods observing the magnetospheric cusp regions, fundamentally changing how we monitor space weather. In other news, SpaceX is targeting May 21st at 22:30 UTC for the maiden flight of Starship version 3, also called Flight 12. This launch, the first from Orbital Launch Pad 2 at Starbase Texas, is an operationally significant step in the company's long-term exploration goals and its preparations to support the Artemis 3 mission in 2027. In a wonderful example of collaborative science, NASA has also opened a new citizen science project called Shock Detectives. This initiative invites volunteers to help analyze more than a decade of magnetospheric shock data gathered by the Magnetospheric Multiscale mission. The mission has collected far more information on these complex regions than any single team of scientists could process on its own, making public participation essential for discovery. Finally, we turn to the planet's tropical oceans, where the story is defined by a conspicuous quiet. The National Hurricane Center forecasts no tropical cyclone formation in the Atlantic, Eastern Pacific, or Central Pacific basins over the next 7 days. This lack of activity is itself a meaningful part of the larger narrative, especially given the warming ENSO trajectory and high temperatures in the Atlantic's main development region. The conditions that historically foster early season storms are partially in place across the warm Atlantic and East Pacific basins. The current absence of activity is therefore a noteworthy calm, but it offers no guarantee that storms will not develop rapidly as the calendar moves deeper into June and July. A profound quiet has settled in, much like the stillness within the synoptic pattern described earlier. Yet, this is a tranquility that feels temporary, one that may not endure. In the near-Earth environment, the closest asteroid approach within the next 7 days will be from the object designated 2026 kf. On May 22nd, at 1:15 UTC, it is projected to pass at a safe distance of 1.71 lunar distances, which is approximately 657,000 kilometers from our planet. This small asteroid, with an absolute magnitude of 26.1, will travel at a relative velocity of 14.06 kilometers per second. Crucially, no objects are forecast to pass inside the Moon's orbit during this period. We recently explored the challenges of planetary defense and detection capabilities, particularly concerning the sunward blind spot in a previous Calm Space segment. The purpose of including this asteroid data today is not to raise alarm, but to do the opposite. It is to confirm that, from a close approach standpoint, there is nothing out of the ordinary that might compete for our attention, thereby leaving the atmospheric story as the day's central focus. This sense of calm extends across nearly every other domain we monitor. The geological signature is normal, and while the volcanic signature includes ongoing observation of the Black Diamond Pool, there is nothing that could be considered acute. Space weather is quiet. In space news, the primary developments are the SMILE launch and preparations for Starship Flight 1-2. The tropical weather signature is also quiet, as is the broader asteroid signature. On any other day, a major development in any one of these areas would likely be the leading story of a brief. Today, however, they all recede into the background, overshadowed by the sheer scale of the atmospheric event. This very absence of competing headlines is, in its own way, powerful evidence of just how unusual the current weather situation truly is. It creates a vacuum of other news, forcing our focus onto the singular, unfolding drama in our atmosphere. With this context established, let us now pull back from the raw data and explore something equally important: how this event will be presented to the wider public over the coming days. The narrative framing an event receives in the broader media landscape is profoundly significant. This framing not only shapes what people believe happened, but it also influences what they think the event implies for the weeks, months, and years ahead. Understanding these different narratives is key to understanding the event's lasting impact on our collective consciousness. Within the broadcast meteorology community, on major networks and cable channels, the event will almost certainly be framed as two separate, though concurrent, weather stories. The coverage of severe weather will concentrate on the signature of large hail in Texas and powerful winds across the Ohio Valley, visualized with familiar tornado tracker graphics and warning crawls. By the evening news, this will likely be followed by a quick update on power outages. In parallel, the heat dome coverage will focus on record-breaking temperatures along the I-95 corridor, featuring graphics that highlight which cities broke or tied their daily highs. A brief mention will be made of the Wednesday cold front that is expected to bring an end to the heat wave. While these two stories will be presented as adjacent segments in the same broadcast, they will not be connected as two faces of a single, massive atmospheric wave. The synoptic scale physics that bind them together is a level of detail that the fast-paced broadcast format rarely has the capacity to explore before needing to move on to the next story. The framing on social media will be entirely different in its character and impact. Here, the complexity of the day will be compressed into a sequence of dramatic, single-frame images and short, arresting video clips. These will include radar loops of the severe weather corridor, surface observation maps displaying the simultaneous temperature extremes, and powerful photographs of property damage in West Texas from the giant hail. We will also see compelling time-lapse videos capturing the arrival of the cold front on Wednesday. The dominant narrative on these platforms will likely lean heavily on the word convergence. We can expect to see posts arguing that this day proves something is fundamentally wrong, that the atmosphere has crossed a critical threshold, or that the configuration of events is unprecedented and its timing suspicious. Some of these posts will be made in good faith by individuals who are correctly observing that today is highly unusual. Others, however, will be made in bad faith by those seeking to attach their own agenda to the event, a challenge inherent to the digital public square. Meanwhile, the climate attribution community will offer a third, more methodical framing. Their work will be a careful analysis that situates today's event within the broader context of a changing climate baseline. It is likely that the World Weather Attribution Group, a rapid attribution team known for its post-event analyses of major heat events, will produce a quick-look study within a few weeks. This analysis will probably conclude that today's event was made both more likely and more severe by human-caused climate change. The magnitude of this attribution will likely fall within the range established by recent studies on other heat events, that is, an increase in probability by a factor of 2 to 10 for an event of this magnitude in our current climate compared to the pre-industrial era. It is important to note what this analysis will not do. It will not, by itself, resolve the open scientific questions about wave amplification frequency, soil moisture coupling, or aerosol unmasking. It will simply and powerfully place today's event within the larger story of a climate that now produces these extremes more often. In the political and policy environment, the framing will be contingent on the relentless churn of the news cycle. If other major stories emerge, this atmospheric event might receive a day or two of coverage before fading from view. However, if the news landscape remains relatively open, it could command attention for a week, extending through the passage of the Wednesday cold front. The dramatic temperature crash could even generate a second wave of coverage. As the story shifts from oppressive heat to atmospheric whiplash, this political coverage will likely sidestep the underlying physics. Instead, it will engage with the tangible policy implications, such as the stress on the energy grid, the effectiveness of public health responses, and the pressing infrastructure investment questions that this cumulative pattern of recent extreme events continues to raise. Ultimately, the framing that the broader public, the 90 million Americans living within the footprints of today's weather systems, will remember in a week's time depends entirely on what happens next. If the window between May 25th and May 28th produces another event of comparable scale, then today will be remembered as the first chapter in a sequence. But if that period brings only modest weather, today will be recalled as a single, dramatic, and isolated day. The persistence of the memory and the narrative that crystallizes around it is therefore contingent on what the atmosphere delivers in the near future. The framing that we aim to provide here on Calm Space is the one that connects these disparate pieces. The synoptic scale perspective that broadcast formats often do not have the space to explore. Today is not two separate weather stories unfolding side by side. It is one story, with two distinct expressions, driven by a single, powerful, atmospheric wave. To truly understand its significance, we must see it not as a collection of isolated events, but as a unified whole. The weather system unfolding today represents a single event with several distinct operational phases. Its primary engine is a powerful Rossby wave, characterized by its high amplitude. This is not an isolated occurrence, but rather the latest in a series of similar wave patterns that have been organizing across the planet over the last few weeks. Understanding this event, however, requires looking at the broader physical context. Several underlying factors are at play, each contributing to the system's intensity. These include the most severe drought signature in the modern instrumental record, a warming North Atlantic Ocean that may be partly due to the unmasking effects of reduced aerosol pollution, and a soil moisture deficit that is actively amplifying the heat within the wave. Furthermore, the El Niño Southern Oscillation is currently shifting from a neutral state toward an El Niño phase. The convergence of these elements has created an atmospheric regime far more capable of producing compressed, multi-hazard events than our historical baseline would suggest. This emergent regime is likely to continue generating events of a similar magnitude for at least the next several months. In a sense, today serves as a calibration. The atmosphere is demonstrating what it is capable of producing at the specific orbital position of the 19th of May, 2026. The next event, whether it arrives in the May 25th to 28th window or later, will be a test of this regime's persistence. Subsequent events over the summer and fall will reveal how the regime is evolving as the ENSO transition progresses and the soil moisture deficit either deepens or begins to recover, depending on future rainfall. This brings us to a fundamental question, one that is asked on calm space more than any other. Is what we are witnessing in our daily weather the new normal, or is it merely a temporary aberration? The most honest answer is that the science has not yet reached a point where it can offer a confident, decade-scale forecast for the frequency of these intense, multi-hazard events. The evidence we do have, however, points in a consistent direction. The Kornhub papers, for example, identify an increase in frequency. The Hansen aerosol hypothesis presents a plausible mechanism for some of the underlying changes. The Williams Megadrought Attribution Study confirms a baseline shift in soil moisture conditions. At the same time, the ENSO trajectory is moving toward a state that has historically been associated with more extreme weather. While the combination of these signals strongly suggests a future with a higher frequency of such events, science cannot yet tell us if today is the new average, or if it is an outlier at the upper end of a distribution that has shifted, but perhaps not as dramatically as today might imply. What can be stated with operational confidence is that this event is happening. It is unusual, and it is precisely the kind of event that scientific literature has been describing as likely to become more common. This is the most truthful framing available. An audience seeking a definitive, black and white answer will likely be disappointed, as the science simply isn't there yet. But for the audience that values the data, the context, and the honest presentation of open questions, this is the space we have built. When events of this scale occur, they often inspire alternative explanations, and it is important to address these ideas directly rather than dismissing them. The audience of this channel knows that we prefer to engage with these claims using the lens of operational physics. Over the next few days, several theories will likely circulate, generally falling into 4 categories. Let's walk through each one, armed with the scientific facts, so you have a clear understanding when you encounter these claims elsewhere. The first explanation that will almost certainly appear is the theory involving the High-Frequency Active Auroral Research Program, or HAARP. The claim posits that the United States government, using the HAARP facility in Gakona, Alaska, is heating the ionosphere with powerful radio waves to create or intensify weather events on the surface. The HAARP facility is indeed real. It is operated by the University of Alaska Fairbanks and is used for ionospheric research. Its experiments are documented and published in peer-reviewed atmospheric science literature. The facility operates with a transmitter power of approximately 3.6 megawatts, focused into the high-frequency radio band, which does produce measurable heating effects in the ionosphere that can be detected by instruments like ionosondes and incoherent scatter radars. The facility is not a secret, and its work is a matter of public record. The fundamental issue with the HAARP weather control claim lies in a simple yet profound mismatch of energy. The arithmetic simply does not add up. A continental-scale Rossby wave, the kind driving today's complex weather event, involves the daily movement and reorganization of approximately 10 to the 25th joules of energy. That is a 1 followed by 25 zeros. In contrast, the HAARP facility, if it were to run continuously at its maximum power of 3.6 megawatts for a full day, would output approximately 3.1 times 10 to the 11th joules. A 2024 paper by UAN, published in Atmospheric Chemistry and Physics, lays out this calculation in detail for anyone to verify. The ratio of the energy required to steer the Rossby wave to the energy HAARP can produce is about 100 trillion to 1, a factor of 10 to the 14th. The physics does not support the claim. Even if HAARP ran at peak output for 100 trillion consecutive days, it would not generate the energy needed to drive a single day of the atmospheric configuration we are seeing now. The disparity is not small. It is a staggering 17 orders of magnitude. A second explanation that is likely to circulate is the cloud seeding theory. This claim suggests that cloud seeding operations, conducted either by government agencies or private companies, are responsible for producing or amplifying the patterns of precipitation or lack thereof associated with today's event. Cloud seeding is a real and established technique. It is used operationally in many places, including the western United States, where various programs seed winter storms over watersheds to increase the accumulation of snowpack. The method works by introducing condensation nuclei, typically silver iodide particles, into existing clouds. This process can slightly boost the precipitation efficiency of those clouds, resulting in an operational enhancement of roughly 5 to 15% more precipitation than the cloud would have produced on its own. However, the limitations of this technology reveal a clear mismatch with the claims made about it. The technique only works on clouds that already exist and were already producing precipitation. It cannot create clouds from nothing, and more importantly, it cannot generate the vast, synoptic-scale atmospheric patterns that are responsible for forming those clouds in the first place. The geographic scale of cloud seeding is inherently local, or, at most, regional. It simply does not, and cannot, produce effects on a continental scale. The mechanism itself is mismatched for the task of creating or steering the massive weather systems we are currently observing. The continental weather pattern we see today is shaped by a wave number 5 to 7 configuration, an atmospheric structure so vast that no cloud seeding technology on Earth possesses the capability to alter it. Inevitably, this leads to other explanations, including the theory of chemtrails. This idea posits that aircraft are intentionally releasing aerosols to manipulate weather. While it is true that the aviation industry's jet engine combustion produces aerosol emissions, a fact documented in peer-reviewed science for its minor climate impacts, the scale of this effect is crucial to understand. The total mass of these aerosols from global commercial flights is several orders of magnitude smaller than the amount required to generate a weather pattern on a continental scale. Furthermore, the geographic layout of flight paths does not align with the footprint of today's anomaly. These two critical mismatches, in both quantity and location, effectively rule out this theory as a driving force for an event of this magnitude. This mechanism is also entirely separate from the aerosol unmasking hypothesis, which concerns the planet-wide removal of marine sulfate aerosols due to international maritime regulations, a completely different process operating on a different scale. A fourth explanation that often surfaces involves the sun. This theory suggests that solar activity, such as the coronal mass ejection from May 16th that triggered a recent geomagnetic storm, is the primary driver of the atmospheric patterns on the surface. While some research, like the 2020 Marchitelli paper in Times Scientific Reports, has identified a weak statistical link between solar variability and the timing of seismic events, the paper does not extend this argument to large-scale atmospheric forcing. Similarly, the Mizuno Cow UMO preprint from 2026 explores related correlations. However, the energy coupling pathway from the Sun to the troposphere, the lowest layer of our atmosphere, is well understood in the scientific literature. The connection is simply too weak to produce the kind of powerful, continent-spanning signature we are witnessing today. The glancing blow from the May 16th coronal mass ejection has almost no direct bearing on the current heat dome or severe weather outbreak. In this instance, the story of space weather and the story of our surface weather are unfolding independently. When encountering claims about today's weather, it is helpful to hold a particular frame of reference. This atmospheric pattern is not a sudden surprise. It is the operational verification of a setup that has been visible in forecast models for a week. The physics contributing to it are well understood at both the synoptic and mesoscale levels. The story is compelling not because the mechanism is a mystery, but because the pattern itself is so unusual. The mechanism is a high-amplitude Rossby wave, amplified by a confluence of underlying drivers, including soil moisture, temperature gradients, ocean heat content, and potentially the effects of aerosol unmasking. This process is not secret knowledge. It is detailed in the scientific literature, discussed by forecasters, and visible in the data. What makes this moment so significant, and what is truly worth our attention, is that this known mechanism is now producing events at a frequency that historical records did not lead us to expect. The underlying drivers are all pointing in a direction that suggests this frequency will only continue to increase. This is the real story, and the alternative explanations are but a distraction from it. Let us close by returning to the central question that today's events are asking. If the atmospheric configuration of the 19th of May 2026 is what the eastern third of the United States experiences while the El Niño Southern Oscillation Index is still officially neutral, what might a similar configuration look like in 6 months? This is a critical question, especially when the Climate Prediction Center is forecasting a 61% probability of El Niño development, with approximately 1 in 3 odds of a strong event by the winter peak of 2026 to 2027. The answer, hinted at in the scientific literature, is what we have been building toward. Today represents the maximum operational expression of what a neutral, yet warming, May atmosphere can achieve. The system responsible for today's weather will exit the operational stage on Wednesday and remain absent for about a week. When it returns, however, the ENSO backdrop will have shifted further toward El Niño. In a very real sense, anyone observing these events is watching a calibration. The atmosphere is demonstrating its capabilities at the 19th of May, 2026, position on its journey. The profound question that follows is what it will do at the 19th of September, 2026, position, or the December 19th, 2026, position. We are being shown a baseline, and the future will be measured against it. The recent history of the Oceanic Niño Index, which is the standard NOAA measurement for the state of the El Niño Southern Oscillation, tells us exactly where we are on this trajectory. The data reveals a clear and rapid progression. For the September, October, November 2025 season, the index was at 0.51. It shifted to 0.55, then 0.54, before dropping to 0.37 and 0.15 inches subsequent period. The most recent calculation for February, March, April is positive 0.11 in just 6 months. The index has transitioned from negative La Niña territory into positive, neutral territory that is trending toward El Niño. The trend is one of warming, and the slope of that warming is significant. This is why, as of May 2026, the Climate Prediction Center has issued an El Niño watch. The operational forecast probability for El Niño development by the May, June, July 2026 window stands at approximately 61%. Looking further ahead, the chance of a strong or even stronger event by the December, January, February peak of 2026 to 2027 is roughly 1 in 3. Should a strong El Niño of this tier develop, the set of historical analogues is sobering. It includes the 1877 to 1878 super event, which produced a global famine and a death toll of 50 million people. A catastrophe explored in detail in a previous Calm Space video on the implications of a super El Niño. The relevant point for today is not to relitigate that history, but to understand the trajectory we are on. The atmosphere will have progressively more energy to work with in the coming months. This means the wave amplification mechanism that produced today's extreme weather will have a deeper reservoir of energy to draw upon. The soil-moisture coupling that intensified the heat dome will, depending on rainfall over the next 2 months, either see a slight recovery or deepen further, potentially strengthening the feedback loop. We are moving into a period where the fundamental forces shaping our weather are themselves being amplified, and the results of that amplification are beginning to unfold before our eyes. The fundamental engine of our weather, the temperature gradient between the tropics and mid-latitudes, is undergoing a transformation. As the equatorial Pacific continues to warm, this differential is set to change, altering the atmospheric waves it generates. Consequently, the weather events anticipated for the summer and fall of 2026 will likely emerge from a new statistical reality, one shifted towards significantly higher magnitudes. The precise extent of this increase, however, remains a profound scientific challenge. Current literature does not yet offer a confident long-term projection for the frequency of these complex, multi-hazard events. Yet, several factors point in a consistent direction. Studies, such as the Kornhuber papers, indicate a rise in frequency. The ongoing El Niño transition introduces an additional forcing mechanism, while the existing drought baseline serves to amplify impact. If projections regarding aerosol unmasking prove correct, another layer of intensity could be added. This confluence of factors provides a clear trajectory, a steepening curve toward more frequent, intense events, but not a precise measure of their future magnitude. The honest scientific assessment is not if, but when the next major event will occur, though whether it is in 3 weeks, 3 months, or 3 years is still unknown. What is certain is that another event is on the horizon. The atmosphere has already provided recent, powerful demonstrations of this new reality. Within the past week alone, we have witnessed these complex patterns manifest, from the convergence of a blizzard in Wyoming with a rebuilding heat dome on the East Coast to the event unfolding today. This current system encompasses a severe weather corridor affecting 90 million people, an adjacent heat dome, and an inbound cold front. Looking ahead, the operational forecast community has pinpointed a potential window for the next significant, organized, severe weather outbreak between approximately May 25th and May 28th. Should this forecast verify, it would suggest the current atmospheric regime is stable and sustained. If it does not, it may signal a period of transition. In either scenario, the overarching climatic trajectory points toward more of these compressed, high-impact events. The fundamental question has shifted from times if times they will happen to times when, how often, and with what intensity. Today's event, the 19th of May, 2026, serves as a crucial calibration point in our understanding of this evolving system. It is a tangible demonstration of the atmosphere's current potential. We are witnessing a severe corridor stretching from Texas to Vermont, directly impacting 90 million people. Simultaneously, a heat dome has settled over the I-95 corridor, affecting tens of millions more. The atmosphere is revealing the two distinct faces of this pattern happening at once. It is also showing us the dramatic whiplash of a cold front expected to follow within 48 hours, which will then give way to a period of about 7 days of synoptic silence. This sequence is a verification of a pattern that scientific literature has long suggested would become more frequent. The events of this day establish a new baseline, a standard against which the atmospheric behavior of the coming months will be measured and understood. For those currently within the footprint of the heat dome, it is essential to stay hydrated, seek cooler environments, and check on elderly and medically vulnerable individuals. It is a critical reminder that a temperature of 98 degrees in mid-May has a different physiological impact on an unacclimated population than the same temperature in mid-August. For individuals in the severe weather corridor, monitoring local National Weather Service forecasts for the latest watches and warnings is paramount. In the Central Texas hail corridor, securing vehicles before sunset is advised. Those within the Central United States flood corridor should closely watch river stage forecasts for their local watersheds. And in Southeast Texas, where forecasts from the Houston office anticipate an additional 5 to 7 inches of rain, residents should prepare for the potential escalation of flood watches to flood warnings as the ground becomes saturated. For anyone observing these events and trying to understand why our weather seems to be behaving in unfamiliar ways, the patterns seen today offer a framework for the future. The key is to carry this understanding forward as the next event is coming. The pattern is not an anomaly. It is a new reality, and the scientific literature is converging on an explanation. The atmosphere has been calibrated, and its next major expression will be drawn from the same distribution whose upper limits we have just witnessed. The wave responsible for today's weather will move eastward by Wednesday, followed by a significant temperature drop of 25 to 30 degrees by Friday. A week of relative quiet is expected to follow, but then, in the final week of May, the next wave will likely begin to organize. Forecasters will provide the specific timing of its arrival. Here on Calm Space, our goal is to ensure our viewers are prepared conceptually. By considering the mechanics of what today's event represents, we become calibrated as well. The next time the atmosphere produces a pattern of this magnitude, you will be equipped to recognize it, to ask the right questions, and to know what to observe. This is the value of what we have witnessed together. Thank you for joining this observation. Please remain safe through the rest of the week.